Equation solving also comes up in the context of optimization, right? Think back to calculus. Trying to do an optimization problem, you need to find the function to optimize. You need to take the derivative, set it equal to 0, and solve for x, the critical points. That's an equation solving thing. But how do you know you've got extreme values, a max and a min? In general, you may not. But the extreme value theorem guarantees you will in certain circumstances. Here's the official statement. Suppose f is a function whose domain is a closed interval. You might also emphasize this interval is bounded. Doesn't go off to infinity. This is called a closed and bounded interval. It's an example of something called a compact set, which you will learn to know and love in real analysis. It's continuous on the entire closed interval. Our book writes it this way. F is an element of C of AB. This symbol again here represents the set of all real valued functions that are continuous on the entire interval from A to B. The C stands for continuous. It's actually an example of a vector space as well from linear algebra, because you can add such functions. Add any two continuous functions, you get a continuous function. Multiply such a continuous function by a scalar, you get another continuous function. So it's closed under addition and scalar multiplication. It's also when your operations are function addition and scalar multiplication, satisfies associative property, distributive property, commutative property, etc. It's an example of a vector space. In fact, if you look in your linear algebra book in chapter 4, you will see this example. In this setting, then there exists points C and D in the interval where this set of inequalities is true for all x in the interval. In other words, f of C is the smallest possible output and f of D is the largest possible output. F of C is the global minimum value. F of D is the global maximum value. I'm using the word global. You can also use the word absolute. I prefer global. The book uses absolute. You got a global max and global min values. The global min occurs at C, the global max occurs at D. But how do you find C and D? Can I change the color of my pen? Color. Let's go to blue. Moreover, if f is differentiable on the open interval from A to B, meaning has a derivative for all points in that open interval, then the numbers C and D occur either at the endpoints of the closed interval or at the critical points of f in the open interval. This can actually be even generalized a little bit more. The function actually doesn't have to quite be differentiable in the entire open interval. There could be isolated spots where it fails to be differentiable, and the graph of the function has a corner in it or something. Those spots where the function fails to be differentiable are also called critical points. And the max and min could occur at those points too. So what's in red could be generalized a little bit, but the most common thing is to consider functions that are nice, continuous, and differentiable. Do we need to assume differentiable on the open interval? Couldn't we assume on the closed? Yeah, you could assume on the closed if you allowed one-sided derivatives, but that's like an extra complication that's not necessary to think about. So this is good enough. How do you apply the extreme value theorem to do an optimization problem? You do essentially just what I said. How do I escape? Escape's not working. How do I get rid of my pen? Automatic. Okay. Why is escape not working? My escape's not working. End show. Okay. I'll keep the annotations. How do you use this? You've done this in calculus. Well, we'll do an example maybe with trigonometry. Actually, we considered this example last week. F of x equals cosine of x minus x. We did it to show the equation cosine of x equals x has a solution with the intermediate value theorem. But let's say we're trying to find the global max and min of this. Oh, over the interval, maybe from, what should I pick? I don't know. Negative pi over 3 to positive 3 pi over 2. Find the global max and min. Oh, and we're almost out of time. We started 10 minutes late. I got 10 more minutes I should take, right? I won't do it. Okay, this is a calculus problem. Let me just say, steps are find f prime of x. Second, solve the equation f prime of x equals 0 for solutions in the open interval from negative pi over 2 to positive 3 pi over 2. Those are going to be your critical points. And third is test function values at the critical points and the endpoints. You don't typically do this in optimization problems, but there are some situations where you need to. The global maximum could occur at the endpoints. If you want confirmation of whether the answer is right, you can graph it. You should compare values as well as the fourth step here. Okay. All right. Have a good day.